Okay, it's 33. I think we can start already. Hi, Abhijeet. You can unmute.
Hello.
So it's a pleasure to introduce you to Abhijeet Borkar. He did his astrophysics studies in Pune and then moved to Cologne for the PhD. And after that, he moved to Prague, where he's now. And today he is going to talk us about a very interesting topic, especially for us, which are green pea galaxies, but in a different wavelength range. So radio and X-rays. So you can share your screen.
Yeah. All right. Hopefully you can see the screen.
Yeah.
Perfect. Thank you, Juan Antonio, for inviting me for the talk. And I'm really happy to present our work today. And hopefully in the coming years, I can come and visit your institute and have a discussion in person about this topic and many other topics. Today, I will be talking about galactic gastronomy, which is discussion on green peas and blueberries. So the motivation for this work comes from essentially understanding what happened in the very early universe. So as you might have known from your undergraduate or graduate studies, the universe started in a Big Bang, as the theme song of the TV show goes. It was in a hot, dense state about 14 billion years ago, and then the expansion started. And with the expansion, at the time, the universe was in a bowl of plasma soup, so from which the photons could not escape. And eventually, as the universe slowly cooled down, the plasma became less and less dense, and the photons could finally escape. And that we can still see in the form of the cosmic microwave background, which happened around something like 400,000 years after the Big Bang and around redshift of 1,000. And that kind of began the dark age of the universe, where essentially, as the universe cooled down, most of the protons and electrons got together to form the first atoms. So most of the hydrogen and helium in the universe was formed at that time. And as the neutral atoms were formed, all the photons kind of escaped, and there was no light present in the universe until for a long time. So around like a couple of 100 million years is when the universe cooled down enough and the gas became dense enough that the first stars could form. And as the first stars were evolving and the first galaxies formed, they gave off a lot of intense radiation. And that intense radiation ionized the neutral hydrogen gas that was present in the universe at that time. And that process lasted for quite a long time. And about starting around like redshift of 15 or 20 and ended at around redshift of 6. At that point, the whole universe was fully ionized. So this era is kind of known as the cosmic reionization. And it's one of the most interesting phases of the universe, where the first stars and first galaxies were forming, and also the first black holes were getting active and forming in the centers of galaxies. So understanding how the universe formed and evolved, it's really interesting to study this era of the universe. The universe was reionized by the first galaxies, where the Lyman continuum photons that were coming from the young massive stars or accreting black holes ionized the universe. So on the right here shows simulations of the early universe, and these are different initial conditions for which these simulations were carried out. And you can see that from top to bottom is the evolution of the universe across the time. And as the first galaxies were evolving with first or second generation of stars, the neutral hydrogen kind of was ionized more and more. And eventually by redshift of 6, most of the hydrogen was completely ionized. And what happens in that process is that the Lyman continuum emission heats up a lot of the hydrogen to very high temperatures. And this sort of suppresses the cooling down of the gas, cooling down to form new stars and feeding the black hole and so on. So this kind of suppresses galaxy formation. So this streamlined the process of galaxy formation and evolution for the universe for the rest of the life. And so from that point onward, most of the hydrogen present in the universe is completely ionized. So this era of the universe is really interesting to understand for getting to know what exactly happened in the first few million years to about a billion years of the universe, and how exactly the first galaxies formed and evolved. It's also not completely clear exactly what is responsible for this reionization. Is it mostly the star formation within these galaxies that were responsible, or whether it was the accreting supermassive black holes or intermediate mass black holes that would be present at that time, whether these sources were responsible for the most of the ionizing radiation. And the current consensus in the community is that about 80% of the ionizing radiation was contributed by the star formation processes in the galaxies. So large heavy stars as well as supernova emission was responsible for about 80 to 85% of the reionization, while black holes, accreting black holes, could contribute something up from about 15 to 20% of the radiation. So it's quite important to understand which processes are responsible and how do they contribute in different ways. And until recently, study of the first galaxies was mostly a theoretical subject, where people were studying it more in the form of models and cosmological simulations, how the first galaxies are evolving and affecting the early universe. And there were a few detections of high redshift galaxies at around redshift 6 and 7, with the highest source detected at the time was at redshift 8 with Hubble and ALMA. And now with the advent of JWST, we are able to go much further in the history of the universe and at higher and higher redshifts. So with JWST, we are able to detect sources at redshift 10 or 11 with spectroscopic confirmation. And there are also several candidates which are going up to redshift 12 to 15 also. It's not quite clear whether they are really sources present at that high redshift, or whether they are redshift 5 galaxies that are kind of masquerading as redshift 12 to 15 sources, because most of these sources still have only photometric detections. They don't have any spectroscopic detections. But we are now starting to see a lot of the images of what the first galaxies look like. And these galaxies are mostly low metallicity sources. They are highly compact. So most of them are very small in size. Many of the sources that have the half-light radius of only 50 to 100 parsecs, so they are very small. Most of them are smaller than a kiloparsec in size. And they are highly star-forming galaxies. So they're forming tens of stars per year and undergoing a massive starburst at that time. And it's most likely that they're hosting population 2 stars rather than the population 3 stars. So it's kind of assumed, or from the metallicity of these sources, it's evident that they are not hosting the very pristine first stars, but they are looking at the second generation stars. And it's quite likely that the progenitors of the modern supermassive black holes are already present in these sources. And there have been a few confirmations of very high redshift black holes in the early universe with JWST observations. So here is one example of such a source, which is a 10 to the 7 solar mass black hole present at redshift 8 already. So this was detected from the sample from Sears catalog, and a lot of strong emission lines are detected in this source. And similarly, with different photometric and spectroscopic methodologies, people are detecting a large sample of candidates at redshift 7 to 10 for black holes presence. So what we see is that most of these galaxies have a huge amount of star formation happening in their entire sort of core, as well as surroundings, as well as many of these are also showing presence of black holes. And there is a hint or a hope that most of these galaxies already have at least some kind of an intermediate mass black hole or a massive black hole present in them, and they are active, but it's quite difficult to discern whether they constitute full AGN or not, because it's quite difficult to distinguish between the emission coming from star formation and coming from the AGN. But it's quite clear now that already at redshift 8 or 9, we are seeing strong signatures of AGN activity in these sources. But we do need to study a lot of local counterparts for these galaxies, because primarily JWST observations are quite expensive, although we are getting a huge amount of treasure trove of data from JWST, and it's still going to last for many years. The number of sources we are getting is still quite small, and especially the kind of details that we want to study from these early galaxies is not possible always with JWST observations. And the other issue is that it's not possible to get multiwavelength data for most of these sources. Many of these are quite faint sources. So JWST is the only instrument that is powerful enough to detect them. And in most cases, in other wavelengths, it's quite difficult to understand what these sources are doing. And so if you want to have a more holistic understanding of what these sources look like, how they are behaving, and so on, you want to have a full multiwavelength analysis of these sources. And it's quite difficult to do that with just purely JWST observations. And in particular, radio and X-ray are quite difficult to detect from these sources. Most of the radio surveys are not strong enough, and even dedicated observations will require tens of hours, hundreds of hours on target to even detect some radiation coming from them at redshifts of 9 or 10. And there have been quite a few attempts at detecting sources such as the little red dots, which are similarly early galaxies at around redshift 5 or 6. And most of these sources are undetected in X-rays. So it's quite difficult to get high quality observations with good detections of these sources in radio, X-ray, and other wavelengths. And also, last but not least, is we want to have high resolution information for these sources, and it's not possible to do that with purely JWST. So if you want to understand what these sources are like and how they behave, we want to study some local counterparts which show similar properties, and we can then analyze them in much more detail and get a full holistic overview of these sources. And one of the candidates for these kinds of sources are the green pea galaxies. So these are the galaxies that were first detected in the Galaxy Zoo project. So human volunteers who were manually classifying the images of the entire SDSS catalog, they found these little spherical green dwarf galaxies, and they dubbed them green peas. And then there were many follow-up observations of these sources. So these are one of the prominent candidates as local counterparts for the early star-forming galaxies. So some of the similarities with these sources are that they are low mass sources. So they are about, the median galaxy mass is about 10 to the 9 solar masses. They're very compact sources. So many of them are less than 1 kiloparsec in size, and on the sky they are less than 1 to 2 arcsecond across. So they're very, very compact sources. They're extremely star-forming galaxies. So they're, for such a small galaxy mass, they're forming tens of solar masses per year. Most of these are very highly star-forming. And their metallicities are low. So similar to the early galaxies, they are low metallicity galaxies with subsolar metallicities. And because of their local distance, so most of these sources are between redshift of 0.1 to 0.5, with the median distance of redshift 0.3. So they're quite nearby. So you are able to get more information out of these. And the main green color for these sources comes from the highly ionized O3 line, which is driving the star formation. And the green color primarily comes from that O3 line. And the other thing that has been detected from these sources is a strong Lyman continuum escape. So many of these sources have shown strong Lyman alpha lines, which are similar to the high redshift starburst galaxies, such as the Lyman alpha emitters. And similarly, there is also presence of ionizing Lyman continuum emission detected from these sources with substantial escape fractions. So these seem to be sources which are quite similar to the early galaxies. And these are the only sources from which such Lyman continuum has been observed with a significant amount. So studying these kinds of sources allows us to understand early galaxies quite well. And the other kind of galaxies which are considered kind of the local analogues of green peas are the blueberry galaxies. So these are similarly dwarf galaxies, but these are even lower mass than green peas. So they're mostly 10 to the 6 to 10 to the 8 solar masses. So about 2 orders of magnitude smaller than the green pea galaxies and much more compact than the green peas. And their star formation rate is not as high as the green pea galaxies. So many of them are about 1 solar mass per year, but because their stellar mass is quite low, their specific star formation rate is much higher. So they're actually forming a lot more stars per unit stellar mass than the green peas or normal galaxies, especially. And their metallicities are even lower than what you expect from green pea galaxies. And the other advantage is that they are even closer. So most of these are below redshift 0.1. So these are kind of considered to be the local analogs of green peas. But because of their lower mass and different star formation rate, they are still somewhat distinct from the green pea galaxy. So they are not just simply green pea galaxies that are moved towards the local universe. And the blue color purely comes from the high star formation rate. So there have been quite a few different samples of these green pea and blueberry galaxies in the last 10 years or so. And JWST is kind of discovering some of the early green pea galaxies. So these are in some of the deep images taken by James Webb. You can see the compact red, highly star-forming galaxies, which look almost similar to galaxies. And here is a nice example of such comparison where on the left is a local green pea galaxy, and on the right is an early green pea, which is at about redshift of 6, about 700-800 years after the Big Bang. And they look quite similar. And not just in photometry, but also when you look at the spectra of these sources, they show a very similar optical spectrum. So on the top here are 2 green pea galaxies in the nearby universe. And the bottom 3 in the black line are the high redshift green pea galaxies detected with JWST. And what we see is that the high redshift galaxies are showing similar emission lines as the green pea galaxies, and their properties are quite similar. Although the strength of the lines is not exactly same as what you see in the local universe. So some of the lines are not as strongly detected. So there are some minor differences between the early galaxies and the green peas, but overall they seem to be quite similar sources. Optically, most of the green peas are classified as star-forming galaxies. So in the sample that was created by Cardamone et al., they had about 120 sources, out of which 80 sources are purely star-forming, which are shown here in the left plot as the red sources. About 10 to 15 sources were classified as narrow-line C.1 sources. So these are the blue sources. And few sources were classified as composite sources. So they probably show some kind of Asian activity. And the star formation rate is about 10 solar masses per year. So most of the sources are following the 10 solar masses per year line that is shown by the dashed line in the right plot. So all the star-forming galaxies that are shown in the purple diamonds in the plot, they are all green pea star-forming galaxies. and they are within sort of the scatter of the 10 solar masses per year line, while the black dots are showing galaxies in merging or interacting systems. So these sources are undergoing a lot more star formation than what you see in merging systems. Recently, Fouillette et al. Have created a new 3D classification diagram to distinguish star-forming galaxies from various kinds of AGN sources, where they include the oxygen 3 to oxygen 2 line ratios and neon 3 to oxygen 2 line ratios, as well as the luminosity of the oxygen 3 line as the classifiers for star-forming galaxies and AGN galaxies. And what they find is that although they are able to distinguish normal star-forming and AGN galaxies very well, the green pea-like sources are all classified as AGN in their sample. So that was kind of interesting thing that detect that essentially all of the green pea-like sources, like the green peas from Cardamone et al., as well as gray peas and purple grapes, which are slightly higher redshift sources compared to green peas, they were all classified as AGN. Although when they looked at their spectra, they do not find any other AGN signatures like the neon 5 line or helium 2 line. They also find that their spectra are quite similar to Wolf-Rayet galaxies, but they also compare the luminosities and spectra to local galaxies, and they find that none of the local Wolf-Rayet galaxies have such high oxygen 3 luminosities. So it's not quite clear exactly what's going on in these sources that creates such a dichotomy in there that they're not able to fit into one category easily. And it seems like they could be one thing or the other quite. So they might have some presence of AGN or maybe not, and it's quite difficult to detect exactly what's going on. So a few years ago, some of our colleagues decided to look at the green pea galaxies in X-rays, and they selected 3 sources for X-ray follow-up observation. So these 3 sources were dubbed green pea 1, 2, and 3. And these were the sources with the highest possibility of detection in the X-ray. So these had the highest star formation rate and lower redshift, so that they would be able to detect these sources easily. And so these sources had star formation rates going from 20 to 60 solar masses per year, and the metallicity was similar to the median metallicity of the green pea galaxies. And all of these sources were classified as purely star-forming galaxies. And through the X-ray observations, they detected X-ray emission for 2 galaxies. So green pea 1 is shown on the left here, and it was detected in the soft X-ray. So below 2 keV, it was quite well detected, as you can see here. But it's not detected that well in the hard X-rays, while the green pea 2 galaxy is quite well detected in the harder X-ray region. So it's in the full X-ray band, here in the middle part, is detected in all 3 X-ray bands, and it shows one of the strongest X-ray emission. While the green pea 3, although it has similar optical properties, it's completely undetected. And we also had a follow-up observation for green pea 3 to go even deeper, and that still does not show any clear detection. So even though all their optical properties are quite similar, their X-ray properties are quite different. And what we also find is that the green pea 1 and green pea 2, not only are they detected very well in X-rays, their X-ray luminosity is also 5 times more than what you expect from luminosity star formation rate relations, as well as their total luminosity is also much higher than 10 to the 42. So if you talk to any AGN X-ray astronomy people, they will tell you that, yeah, these are obviously AGN candidates, that normally from purely star-forming galaxies, you don't get this high, especially in the dwarf galaxies, you don't get this high X-ray luminosity, and especially 5 times more than what is expected from the luminosity and star formation rate relation, even accounting for the metallicity of these galaxies. So here on the plot, you can see that green pea 1 and green pea 2 are significantly higher in luminosity, while green pea 3 is consistent with the prediction from star formation rate. And here we are also showing the comparison with the luminosity versus the star formation rate and metallicity relation, and comparing with the similar kind of analog galaxies. So Lyman break galaxies and star forming galaxies, as well as green pea analogs. And what we find is that even comparing with these kinds of sources, the green pea 1 and 2 are much brighter than X-ray brighter than what you expect from similar kind of Lyman break analog sources. And when you look at the mid-infrared classification of these sources, what we find is that there are different. So on the right, we show from Satyapal et al. Different classifications that are used for classifying sources from star formation and AGN sources. And there are different wedges used or different lines to distinguish between AGN and star forming candidates. And we show here on the left that GP1, GP2, and GP3, all of them are classified as somewhat star forming and somewhat AGN-like. Especially GP1 is kind of on the borderline between AGN and star forming galaxy, while GP2 and GP3 seem to be clearly AGN-like sources, which is kind of strange that their X-ray properties are completely different, that GP2 is very well detected and GP3 is not detected at all. And it was similar in the BPT diagram also, that GP2 and GP3 have similar optical emission lines in the BPT diagram, while GP1 shows slightly different. But in X-rays, GP1 and GP2 are detected, but the third source is not detected at all. So it's kind of confusing exactly what's going on in these sources. Other people have done similar analysis for green pea galaxies, and they have found that when you look at mid-infrared colors of green pea sources, they detected, when you look at also the variability in mid-infrared, they found two sources which were quite significantly variable. So the mid-infrared classification can allow you to detect AGN in green pea-like sources. So there seems to be some green peas which have AGN presence in them, as seen from this paper from Harish et al., where they find two sources out of their sample where they detect AGN activity. And similar kind of AGN presence has been detected in local dwarf galaxies. So NGC 4395 is the famous local AGN with an intermediate mass black hole that is quite well known. Along with that, there are several systematic studies that have been presented. So another famous one is the Hennis 210, which is a candidate AGN, although it's not intermediate mass black hole, it has a lower mass estimated black hole present in them. And there are quite a few other analysis that people have done, including, for example, Reines et al., who have used radio observations with VLA, so high angular resolution radio observations, to study local dwarf galaxy sample to detect several AGN candidates, which are not only intermediate mass black holes, but also are offset from the center. So these were dubbed as the wandering black holes that were detected in their analysis. So along with that, Burchell et al. Have also used X-ray observations of dwarf galaxies to find AGN candidates. They were detected from high X-ray flux, and they also find that the AGN candidates from local dwarf galaxies show about 85% of them show disagreement from their BPT classification. So it seems like when you're looking at the dwarf galaxy population in the local universe, their optical classification may not always agree with what you see in other wavelengths. And so to go more into details of these sources, one way you can look for AGN presence is with radio observations. And we applied for VLA observations of the three sources that we had X-ray observations for. And we detected both GP1 and GP2 with strong detections in both 6 gigahertz and 10 gigahertz observations, while GP3 was not detected at all. And this is quite similar to what we see in X-rays also, that GP1 and GP2 are strongly detected, while GP3 is not detected at all. So this is kind of showing that there is quite similar relation happening between X-rays and radio, while the optical seems to be showing something different. And it could be that the population of electrons or particles and the sources which are responsible for radio and X-ray emission are quite same. So if it is presence of an agent, it's probably the same agent that is giving rise to the radio emission as well as X-ray emission. We also looked into the archival observations of these sources, as well as looking into different radio catalogs for their detection. And again, we detect Green P1 and Green P2 very clearly in many of the archival data sets, while Green P3 is not detected in any of them. So even with some of the highest sensitivity data sets like LOFAR and VLAS, as well as some of the targeted observations that have been conducted by people with GMRT, for example, they were not able to detect any of these sources, the GP3 source at all, while GP1 and GP2 are very clearly detected. And when we plot the radio spectrum of these sources, the spectra show a characteristic synchrotron spectrum with the spectral index of about 0.7 up to 0.9. So this is consistent with the emission coming from synchrotron radiation that could arise from, excuse me, from star formation, or could be arising from AGN. So it's not easy to distinguish whether it's coming from purely from an AGN or not. What we also did was that we looked at the overall sample of the green pea and blueberries that are present in the literature and looked for how well they are detected. So what we wanted to do was to compare whether the GP1 and GP2 that we detect, are they kind of prototypical green pea galaxies, or they are somehow special compared to the overall sample of the green peas and blueberries. And what we find is that when we compare the 150 megahertz luminosity detected from LOFAR for these sources and plot them against the star formation rate, most of the sources are not detected at all. So even though from the purely star formation rate to luminosity relations that are established for local galaxies, so the red dashed line here shows the relation that is established for normal galaxies in the local universe. If we assume that relation, almost 75% of the sources should be detected in the LOFAR dataset, but only 40% of the sources are detected. And as you go towards the lower star formation rate and lower black hole, lower galaxy mass, so for example, the purple and blue sources are the blueberry galaxies, while the green and orange sources are the green peas. And most of the blueberries are completely undetected, even though they could be detected with LOFAR. And even accounting for metallicity and few other relations, which are shown by the black dotted line, they are still 1 to 2 orders of magnitude underluminous compared to the established relation. While the detected sources, especially at the higher black hole, higher stellar mass and higher star formation rate, like the green peas shown here on the top right corner, they are consistent with star formation rate, with the exception of this source, which is a quasar candidate that is quite known from SDSS spectrum that it's likely to be a quasar candidate. So that is the one source that is classified in Cardamone sample as a purely star-forming galaxy, but in other classifications, for example, in mid-infrared, it's classified as a AGN or quasar candidate. So that's the only source which is very bright in radio. And the other source that is detected in the LOFAR sample is the green P1 shown here in the star, and that is also consistent with star formation in radio. So the other thing that we also looked at were the sources that were detected in Cardamone sample as narrow line Seafoot ones. And all of these sources are very brightly detected in almost all archival radio surveys. So most of these sources show very strong radio emission and are detected in almost every catalog which has a significant sensitivity. So it seems that if the sources are AGN like sources, then they will show very strong radio emission. But just because a source is consistent with star formation, it might not be purely star forming galaxy. That because most of the sample shows that they are 1 to 2 orders of magnitude underluminous, any source that you detect consistent with star formation, that could still be one order of magnitude brighter than the overall population. And what we need right now is to actually have a large sample of dwarf galaxies at lower star formation rate and lower stellar mass, and establish new relation for these sources that are purely derived from these low mass galaxies, and not just extrapolate these relations that are defined for high mass normal galaxies with normal star formation rate. So once we have these kinds of relations, then it will be much easier to distinguish whether the sources which are detected in radio, whether they are star forming or whether they show any presence of AGN. And this is not the first time it has been detected that dwarf galaxies have lower luminosity in radio. There have been several observations in the past of green pea-like galaxies as well as general dwarf galaxies. And they have shown that radio emission in these sources is much lower than what is expected from star formation, and dwarf galaxies are in general radio underluminous. And there are several reasons that could lead to that. That essentially the dwarf galaxies are much smaller in size, and so it's easier for the synchrotron emitting electrons to escape the gravitational bound of the galaxies, and so not entire energy from these electrons is converted into synchrotron radiation. So you're not getting a pure one-to-one correlation between the luminosity that you detect and what is the presence of star-forming electrons. As well as it could also be that in these dwarf galaxies, the magnetic fields are much weaker, or they're not as smoothly aligned. So if you have that kind of chaotic magnetic field or unsettled magnetic field, that can also lead to synchrotron losses and escape of electrons, and that can suppress the radioluminosity in these sources. So it's quite established now that these sources are significantly underluminous. So if you see sources which are consistent with star formation and are very low star formation rate and low stellar mass, they might be hosting still a massive black hole in their center. Along with that, what we were also working on recently is looking at the further observations of some of the Blueberry galaxies. So we applied for a few more observations of Blueberry galaxies. So 8 sources were applied for, and about 6 sources were observed in that. So these are shown here in blue as BB1 to BB8. And again, what we find is that majority of the sources are very underluminous. Only BB1 and BB8 are detected, and BB1 seems to be consistent with expectations from star formation, while all the other sources are significantly underluminous, almost 1 to 2 orders of magnitude underluminous. And GP1, GP2, and BB8 seem to be much higher than expectations from star formation. So it's quite likely that these are showing some presence of a massive black hole and active black hole in their centers. And we consider these to be Asian candidates. So this work is currently under review, and hopefully you might see it on arXiv in the next coming months. And lastly, one of my colleagues is working on a new sample of blueberries. So to sort of increase the number of green pea and blueberry-like sources and understand the overall properties, especially in optical and mid-infrared. So he identified 88 blueberries, out of which 40 are new sources. And these are some of the most intensely star-forming sources that are known in the local universe. The sources are much bluer in optical, as well as they show a lot redder colors in the infrared. And they're all classified as star-forming sources, with exception of one source, which is very bright in radio and is likely to be an Asian candidate. The metallicities of these sources are quite low, and they also have much higher extinction present. And some of these sources also show some kind of merging activity or some interactions going on. So this work is also accepted recently, and you can find it on arXiv. So I would like to conclude the short presentation I had. So the main conclusion I have from the analysis of 3 green pea galaxies we have is that these are sources which are classified as star forming in the BPT diagram, but in other kinds of classifications, they have very conflicting interpretation. So the new classification with mid-infrared color shows that they are likely AGN. The X-ray observations show that they are very high luminosity sources. So 2 of the sources have very high luminosity, while the third is completely undetected. And the X-ray excess is 5 times more than what you detect from star formation rate. And that is very significant sign of AGN activity in their center. And most of these sources, these cannot be explained by purely stochasticity or a large number of high mass X-ray binaries, or even the presence of hot gas or different star formation rate and metallicity. These things cannot explain the high X-ray luminosity in these sources. The likely explanation for high X-ray luminosity is either presence of a massive black hole in the center that is actively accreting, or a presence of an extreme ULX or supernova or multiple supernovae that are going off at the same time that are creating such high X-ray luminosity. And similarly, these the same 2 GP sources are detected in radio, but they seem to be consistent with star formation rate, while the third source is undetected. And it's similar to what we see in X-rays, that the 2 sources are detected and they're strong, while the third source is completely undetected. And their optical, mid-infrared, X-ray, and radio classifications and properties are also quite different, where in optical and mid-infrared, GP2 and GP3 show similarities, while GP1 is kind of an odd one, while in radio and X-rays, GP1 and GP2 show similar properties, while GP3 is the odd one. So looking at the same source at 4 different wavelength regimes, we get a completely different picture in them. So it's not quite clear what's going on in these sources, and much further analysis and overall an analysis of a full green pea and blueberry sample is needed to understand the significance of the X-ray and radio emission in these sources and whether these are showing AGN candidates or not. And a general take-home message is that these green peas and blueberries are good local analogs for the first galaxies. They might not be exactly identical to the first galaxies, but they show some very good similarities with the early galaxies, so that we can study them to understand what was going on in the early universe, how the first galaxies were forming and evolving, and what was responsible for the reionization of the universe. The other conclusion that we draw from our analysis is that classifying these low mass, low metallicity dwarf galaxies, which have high star formation going on, is very complicated. It's difficult to identify AGN mechanisms in them, and different classifying mechanisms give very different results. So it's really important to have a full multi-wavelength view of these sources. And you cannot simply just look at one wavelength for these sources. For example, just observing 10 galaxies in X-rays or in optical and declaring that these are purely star forming or purely AGN sources. So it's important to look at these sources holistically. What we also find is that majority of these galaxies are significantly underluminous compared to the luminosity star formation rate relations, both in X-rays and radio. And essentially, these relations need an update. Most of these relations are built on what is already detected, and the undetected sources are kind of not included in the established relations. And also they are often defined for normal galaxies, so they may not be as applicable for these kinds of highly star-forming dwarf galaxies, which have lower absolute star formation rate compared to normal galaxies, but they have extremely high specific star formation rate. So what is needed is also an update of these luminosity star formation rate relations. And if we detect strong X-ray and radio emission in these dwarf galaxies, they could indicate presence of a massive black hole that is actively accreting. So I thank you all for attention, and I'm happy to have discussion.
Thank you very much, Abhijeet, for the very nice talk. I'm sure we have some questions. Andres?
Yes, thank you so much.
You're in front of the camera.
Exactly. Very nice talk. I learned a lot. I have a very well, maybe very naive question. So about the differences between the GP1, GP2, and 3. I mean, what would be your next step? Because to me, it seems like you tried almost everything. Like, are you gonna continue digging into why are they so different?
Yeah, I think so. One of the things that we would like to do is to get some near-infrared and mid-infrared spectra of these sources to see whether we detect any strong emission lines in them. If we do that, so having JWST observations will be a very nice bonus. And if we detect any strong emission lines in them, that could indicate strongly that there is a AGN presence in them. But yeah, as you say, we have tried almost everything and it's quite difficult. One thing that we wanted to try with our radio observation that we were not able to do was to get high angular resolution observations. So currently our observations are with low angular resolution, where the source is not resolved at all. So if we apply, we had applied for high resolution observations, but because it was sea level observation, we were not able to detect, we were not able to get the observations for that. Only the low resolution observations were completed. So one way to find presence of an AGN would be to get high resolution radio observation, which are able to sort of resolve out the extended radio emission coming from star formation rate. And if you have a presence of a central black hole that is compact, and we are able to resolve it out over 3 to 5 PSF or synthesized beams, then that would strongly indicate presence of an AGN. While if we detect purely resolved emission in high resolution observations, then that would clearly say that this is star forming galaxy and not showing any indication of AGN. But I think also the other thing that we need to do is to study these sources in a more and larger sample. So currently in X-rays, especially, we have only about 10 sources which have had nice X-ray observations. Most of these have only 10 to 20 kilosecond observations in X-rays. So getting a larger sample with decent 20 to 50 kilosecond observations so that we can get strong detections in these sources and verify what kind of general population looks like and whether our sources are anomalous compared to the general population. That will be able to establish that, yes, something different is going on in these sources compared to the overall population.
Thanks.
And variability, have you checked for variability? Because these are smaller black holes, they should vary in a shorter time.
Yeah, that's a great idea. And that is something that we are also considering, although many of these sources don't have multiple observations. So we were not able to look for variability in these sources. But yeah, that is also another thing that we are planning to do in the next, to look for either multiple observations of these sources and to see whether they show any variability.
Questions? Ricardo?
Yes, thank you very much for your nice presentation, Abhijeet. I was also wondering about the differences between the 3 galaxies that you have X-ray emission. Since we know that these objects, both green peas and blueberries, are selected, I mean, regardless of the cardamones and the other authors that selected by morphological classification, but these objects are all of them very high equivalent width, so very extreme in the optical emission lines. So this means that they are very young starbursts.
Yes.
With very high ionization conditions. So I was wondering whether these 3 galaxies have any difference in ionization and also in mean likewise the stellar ages. So the starburst ages that you can infer from the emission is different.
Yeah, I think so. We have looked at the equivalent widths of these sources, and they are consistent with the overall population. So they don't seem to be outliers in that sense. The only thing that they were selected for our observations was that they had the highest star formation rate and the best detectability in X-rays and radios. But otherwise, their properties were quite similar to other sources. And with the age, I have not looked into that, but one of my colleagues is looking into the ages of the stellar population. And most of these are less than 10 mega years old, but it's also quite consistent with the overall population that these are not extremely young or extremely, so these are not more young or old compared to the overall sample.
So one suggestion it could be, I mean, I completely agree that in order to disentangle this AGN starburst contribution, it's essential to have a larger sample. And one way to collect a large sample could be instead of using specific star formation, right? Just using equivalent width or any other emission line diagnostic.
Yeah, so
I'm saying that we have been working with these objects quite a lot. Also, for instance, the low redshift Lyman continuum survey.
Yeah,
we have seen that there is between 0 and 10 mega years, there is a lot of scatter in the optical and in the multiwavelength properties.
Right.
So, for instance, in radio, we have recently published a paper by Omkar and Byte showing that there is a variety of radio SEDs for these Lyman continuum leakers, weak leakers, strong leakers, and so on. So I think it will be very interesting to enlarge this kind of samples using a variety of these objects selected by different properties, especially for emission lines.
Yeah, that's a great shout. The recent work that has been published right now by my colleague, if you can have a look at this paper, Korompatzakis et al. So this one, we were trying to do exactly that trying to detect these blueberry galaxies with a criteria that is more consistent using equivalent widths and a few other criteria. So we are trying to do that also, that, what you mentioned, that having a more stringent criteria for detecting these sources and using equivalent widths and optical colors and so on.
If I may. So I'm a bit also skeptical about the not the X-ray but the mid-infrared. So they're using white colors on these objects, and I'm telling this because we know that very young starbursts could often have a very enshrouded, dust-enshrouded, dust-heated bubble.
Right.
So this will mimic red colors in these diagnostics, as we see, for instance, in very well-known cases in the very local universe. No?
Yes.
PSS. So what's your opinion about that? How we can deal with this this dichotomy in this diagnostic?
Yeah, I think my personal opinion is similar to what you say, that mid-infrared is quite difficult because as even you can see here on the right plot, that it's not a clear distinction between star forming in AGN like galaxies, and this is already for mostly normal galaxies. So for dwarf galaxies, they have higher extinction. The star formation rate is also higher, so you are going to get much more red color present in them. So purely mid-infrared is probably not a good idea to use for selecting these sources, and we probably need, at least if they are really extremely red in the mid-infrared colors, that might indicate it. But if they are just normal mid-infrared color that are classified as AGN in the normal galaxies, that might not be sufficient to classify them as AGN in the dwarf galaxies. And you're completely right that a lot of the star-forming dwarf galaxies mimic AGN-like colors in mid-infrared, and that is definitely not the best way to select these sources.
Thank you.
More questions? Celio?
Curiosity rather than a question. If you could go back to your X-ray observations, please, of the 3 GPs, where basically for GP3 that you say no clear detection. If I look at the 1-2 kV, am I being misled that there is something where it's supposed to be?
Yeah.
In the center, like, is it not associated? Does it not meet certain signal to noise criteria or what? Because like by eye, I would say that is a detection.
Yes. So one of our master students did work on it extensively to see if there is something there or not, and they were not able to detect anything beyond 1 to 2 sigma. So when you look at the overall comparison with the background emission and apply different detection statistics, it does not seem to be more than 2 sigma detection. I think if I remember correctly, it wasn't even more than 1 sigma. So I will have to check that because it was 2-3 years ago that they did the analysis. But yeah, it's not strong detection. So essentially what we have a much deeper observation, but even there we don't detect anything clearly. It's like a weak detection, but it could also be because there is a strong source that is nearby, and it could be some contamination from the nearby source also.
It would be also very strange that it's detected there, but not in any of the other two bands. Because if it's obscure, then it will be detected in the high energies. If it's a soft source, it would be detected here. But just within one band, this is strange. More questions? Also among the online audience, you can unmute yourself and ask.
Yeah, so someone was sending a comment about the BPT diagram or something.
I have another question. Have you looked for, so any of these guys, do they have broad components in the Balmer lines?
I don't think so. They don't have a broad component in H alpha and H beta lines now.
Because that it's also used as a tracer.
Yeah.
And in ALMA, do they have ALMA observations?
No, we are planning to observe with ALMA, so that's going to be a next step. We did not have enough time this year to apply for the ALMA observations, but next year that's going to be the case. We will apply for ALMA observations of several of these sources and understand both molecular gas and dust contained in these sources to see whether we can disentangle some way.
I would also look for variability in ALMA. If you have the chance, because you can have in these millimeter cores, you can have more chances to detect burst or variability. And that will be a tracer, at least of a black hole. Maybe not big, but a black hole.
Yeah, there are also ways of detecting very obscure black holes with ALMA observations with what is known as the HCN diagram. So that is also one thing that we could try, that if the black hole is there, but it's very obscure, that it's visible in some X-ray and mid-infrared, but not in optical, then that could be something that we could try to see in ALMA.
Thanks. I think Ricardo had.
Yeah, just one last question. So regarding the high ionization emission lines like helium-2, so is there any difference between these two X-ray emitting galaxies and the other one? Just to know a bit if so you know that there is a discussion of X-ray binaries and things like that. So have you compared? So if you have detection in these high ionization lines, can you compare with the models?
Yeah, I haven't looked at that part of the spectrum myself, but I think one of my colleagues may be able to answer that. Kostas, do you have idea about that? Yeah, his mic is not working, so he might be able to type in the chat. But yeah, I have not looked at it, so maybe we can get back to you remotely.
Thanks. Any more questions? Not? We thanks again, Abhijeet.
Thank you so much. That was really great discussion. Yeah, Costa says that helium-2 is not observed in these GPs.
No, So thank you very much, Abhijeet, for the very nice talk.
Thank you so much, and hopefully I will come there next time in person.
Visiting us very soon.
Yeah.
And